So we've seen how an integral can help us find the area between two curves. We've seen how an integral can help us find the volumes of solids of revolution. We've also seen how the integral helps us find the volume of a solid with known cross sections. There's also another application of the integral that is helpful, and that application is in our pursuit of finding the length of an arc, a piece of a curve. In the past, you guys have found the distance between 2 points that lie along a line by using the distance formula. And in that distance formula, we had the square root of the difference of the x's squared plus the difference of the y squared added together. Okay, well, we're going to be looking at 2 points that fall on a curve where those 2 points that are on the curve, the end points, the left end point and the right end point, don't fall along a straight line, but we're perhaps interested in finding the length of that curvy piece of the graph. So to do so, let the function given by y equals f of x represent a smooth curve on the interval from a to b. So a is your left x value of your endpoint, and b is your right x value of your right endpoint. The arc length of the function between a and b is given by this formula. So just one more formula that we have to memorize if we're asked to find the length of an arc. And similarly for x equals g of y, the arc length of g between c and d is given by the similar formula here. So just notice the structure here. We have a square root, and then under the square root, the radicand is 1 plus the derivative of the function that we want the length of the piece on squared. So we're going to look at a couple of examples. So you'll find this problem on page 483, and I just picked out problem number 3. Okay, we're going to work with y equals 2/3 x to the 3/2 plus 1. There's a picture in the textbook. I'll go ahead and try and recreate it here. And the y-intercept is going to be 0, 1. And the graph, if you were to graph it, heads up something like this. Okay, and this is the picture that we're given in the textbook. And between these two indicated endpoints right here, okay, we're asked to find how long is it from here to here. We can't use the distance formula because those 2 points don't fall in a straight line, but fortunately for us in calculus, we're going to use the integral to help us find that distance right there. And this formula what it does is it kind of stretches this out and finds the length of this piece all through the integration process. So all we have to do to find that distance from 0, 1 to 1, whatever this is here, okay, all we're going to have to do is use the integral and integrate. All right, so thinking about the formula that I'm going to be using, I need to find the derivative of my equation. So y prime in terms of x. You don't need of x, but it's just helpful to know that there's an x here. Okay, power rule, that gives x to the 1/2, which of course we know as square root of x. So I don't know which format I'm going to need, but you know, just be prepared. All right, so set up the integral. Okay, so the limits would be the x coordinates of the two endpoints. So it appears to be 0 and 1. Square root. And we always start the arc length with 1 plus. Then we want to take the derivative, which is the square root of x, and square it. It's part of the formula. Okay, so I'm really done there. And then let's just evaluate the integral. This would likely be a no calculator question, and we're going to go through it with no calculator. So squaring square root of x squared. Okay, this is just a u substitution problem. It might be helpful to rewrite the square root as a 1/2 power. This is a good time to review u substitution. All right, so u is the inside function, and the derivative is dx. So it doesn't appear that I need to bring anything in, so I'm ready to go to the u integral. So u to the 1/2 du. The 1/2. So I'm going to stop here and just mention that how we would proceed, okay, is that we would do the reverse power rule, change back to x, and then evaluate and get an answer. Well, something new that hasn't been mentioned before, that's a good time to mention it in this problem, is I don't have to go back to x's. And let me show you what I mean. All right, I'm going to go ahead and integrate this reverse power rule. Okay. So that's going to be u raised to the 3/2 multiplied by 2/3. And I'm going to evaluate this. Okay, but I'm not going to evaluate it at 0 and 1. So I'm going to come back over here and make an adjustment. Okay, I'm going to evaluate these at different limits because I don't want to go back to x's. I don't want to plug in 1 plus x and have to work with that. This is kind of simple. So if I'm going to stay with the u and not go all the way back to the x, that means I have to change my limits to u limits. They started out as x limits. Okay, but now it's time to change them to u if I'm going to stay with the u. Okay, well, how do I get u limits? Well, take 0, come back over here. Okay, 0 was x. So when you plug 0 in for x, you're going to get u as 1. So my lower limit here is going to be 1. My lower u limit. Now plug in 1 here for x. So my upper limit is going to be 2. So those are going to be my u limits. I don't want to change back to 1 plus x here for u. It's already pretty simple. All right? So now let's just do some calculations. So 2/3, I'm going to pull that out. Plug in 2 for u. So that's 2 raised to the 3/2. Plug in 1 for u, so that's 1 raised to the 3/2. Clean it up a little bit. Okay, this right here is 2 square root of 2. That's the exponent. If I have 2 of them, then that means 2 comes out, and leaving 1 2 under the radical. And then 1 to any power is just 1. So that's your answer. You could have switched all the way back to the x variable and then used the limits of 0 and 1, and you would have gotten the same answer. But I wanted to provide this alternate way to do the calculations when you're using u substitution. Okay, so the next problem I want to look at is 11. A picture is not given. All that's given for this problem is this information, and you're asked to find the length of the arc that goes from A to B. X coordinate of 0 to the later x coordinate of 2. No pictures provided. So if you wanted to, graph that and get a little visual over here, I mean, from x equals 0 to x equals 2, that wouldn't be a bad idea. I'm going to go ahead and find the derivative. Constant multiplier rule. Go in, find the derivative. Using the little baby chain rule here. Okay, set up the integral. One plus, and right in here, we're going to put the derivative and square it with respect to x. So this whole derivative. You can find this answer without a calculator. It's pretty tedious, I'll tell you. You have to square this quantity, which means you'll have a fourth of whatever you get when you FOIL this. Okay. And then you'd have to get a common denominator with the 1. It looks like you'd have to make it 4 over 4, clean it up, refactor. It's pretty tedious. So right here we're just going to say, you know what? Let's just type this into the calculator and then go to the home, type this into y equals, go to the home screen and use the appropriate keystrokes to find the answer. And when that's all said and done, I like to have more than 3 decimals, but I just kind of stole this answer from the back of the book. You know what, I think this would be a great time for you to pause the video right here and just make sure that you're able to enter this into y equals. I just know that there's several tedious functions that you're going to have to work with and enter into the calculator, and entering it is, is a skill in itself. So you might want to pause, enter this into y1 and see if you get this value. So this is the given information in 13 on this particular page. I don't think there's a picture provided, but I think you guys get the idea. Okay, now you can clearly see this time we're going to be integrating with respect to y, so we need y limits, and it's given to us. So let's find the derivative. This looks like a chain rule. No product rule because I don't have another variable y here. Alright, so just basically the chain rule. Multiplying a third by 3/2 gives 1/2. Leave the inside function alone and reduce the power by 1/2. But don't forget to multiply by the derivative of the inside function, which is 2y. Little cleanup. This is all being multiplied. The 1/2 is outside of this power, so I'm going to reach across here and cancel these 2's. Cleaning it up a little bit, it looks like I have y times the square root of y squared plus 2. Y limits 0 to 4, square root of 1 plus, I'm going to go ahead and use a bracket and dump in the derivative. So just kind of pay attention to the structure. If you're finding arc length, okay, you're going to add 1 plus the derivative. Okay, we want to be sure and do a little cleanup here. This one we're going to actually do without a calculator. It's a little tedious, but not so much as the last one. I'm going to work across a little bit. We're going to take care of squaring that derivative. So when you square this quantity, let's square the y. We're going to get y squared, and let's square the square root, so that's going to be y squared plus 2. All right, let's continue cleaning this up. I'm going to distribute the y squared, so I'll have 1 plus y to the 4th plus 2y squared. As you can see, we're going to rearrange these terms under the radical. And this 4th degree function is factorable. Continuing to work to the side. That's going to factor into a binomial square. Y squared plus 1 quantity squared with respect to y. And that's convenient because you can pull out one of the factors. So a lot of algebra. Notice I haven't lost the integral symbol with the limits. You shouldn't either. Look down, make sure, write down your paper, make sure you have that as well. Okay, pull out the y squared plus 1. Okay, and look how nice that is now to find an antiderivative. Reverse power rules. So going to the antiderivative, I'm going to lose the integral symbol. Okay, and it's all of this evaluated from 0 to 4. Kind of finish with some calculations here. Oh, gotta love that 0 down there, because 0 goes into all terms, and all terms have a y, so that's just going to be that big old 0. Evaluate at the upper limit, so 4 cubed divided by 3 plus 4. Almost there. So cleaning up, 64 thirds plus 4 whole. We're going to want to make that have a common denominator, so that'll be 12 thirds. Final answer, 76 thirds.